So today is November 10th, and you're here for Econ 249. And what you're looking at is a flyer about an event that's happening today, Tuesday, November 10th. Make this a little bigger. So it's about a presentation on decolonizing social sciences. And it's presented by two professors who are not at Queen's College, but it is today from 4:30 to 6, and the Zoom link is here. If you're interested, let me know. I can email you the link. You might not be able to access it on the screen here, but it's something different that you might be interested in. There's another flyer I'm going to share with you. Make this one smaller. So this is presented by the Economics and Business Club, and it is with Professor Feliciano. Some of you might have taken her course in the past, and it will be really interesting. So it's the impact of COVID on international trade, and it's part 2 of a 4-part series. It's going to be held tomorrow for free during free hour between 12:15 and 1:15. Again, there's a link here to join. So if you're interested, let me know. I can send you the link. You should have also received these 2 flyers in the mail, an email that I sent. So one more that I want to share with you, and this is quite important. It's a leadership conference. It's not anytime soon. It's in December 3rd, from 11 a.m. to 4 p.m. I've heard many positive things about this particular conference. There are companies and firms that come and recruit and network, and it's primarily hosted by JP Morgan Chase senior leaders. So it's open for freshmen, sophomores, and junior students from different majors. So you have to register to attend because space is limited. So I will be sending this to you soon. I did not email this to you yet. But again, you should start thinking about internships for summer 21. I know there's not a lot available, and most of them are virtual. But you should start thinking about what you're going to do to enhance your resume. So this is the time to work with firms because they're interviewing and recruiting. So, make use of all the resources that are available to you. I know that a lot has happened since the last time we spoke. It feels like so many things have happened. I'm not going to discuss that. Some of us might say that we have a president, some of us might say that we haven't decided, so let's not talk about that. Let's talk about our chapter 11, confidence intervals, because we need to continue with life, right? So this is the chapter that we were discussing in the last class. And if you recall, what we did in the last class was just this, constructing a confidence interval, focusing on predicting the mean by using a range of numbers, an interval. And we did it specifically for sigma known, meaning when you knew the population standard deviation. So now I'm going to switch to the next set. Let's see. Going down to the next slide. So this is what I'll do in today's class. I'm going to focus on confidence interval, population mean, but now I'm saying that the population standard deviation is unknown. So I'm going to start with a story. And does anyone recognize what this is?
Quality beer.
Quality beer. Or beer, like Alexander said. Okay. So It's Guinness beer, and the reason I put this up is it's stories about Guinness breweries and someone who worked for Guinness Brewery. So this was in the early 20th century, in 1908. There was a mathematician who was actually a chemist turned statistician who worked for Guinness Breweries in 1908. And where is Guinness Breweries?
Ireland?
Ireland, yes. So in my last class, someone said Germany. Someone else
Oh
said,
no.
yeah. So Ireland. Okay. So this was in Ireland, and part of his charge, his task was to um, confirm the level of stout in the beer. And this was apparently at the time, it was not done prior to 1908. So this was a new experiment, and he had to predict the average. So I'm not sure the details, but he had to predict the average amount of stout. Um, and if you recall, in our previous method of predicting an average, a mean, you had to know what the population standard deviation was. You couldn't continue with this idea of estimating using an interval by referring to the normal distribution table if you don't have the value for sigma. So since his experiment was new, he did not know what the population standard deviation was. It was never done before. There's no historical data to refer to. So I keep saying he, and I didn't tell you his name. So his name is William Gossett. So William Gossett had to come up with an estimate. He had to predict what the average was. And since it was never done before, he had to rethink his analysis. He couldn't use the previous method because that formula involved population standard deviation. So what he did is he thought, okay, why not use the sample standard deviation instead? And he couldn't use the normal distribution tables, so he came up with a new distribution, a new different distribution that was sort of based on the normal distribution, but slightly different. And he used the sample standard deviation in his formula and came up with his analysis, and the conclusion was very accurate. His prediction was accurate. And he could even state 99% confidence or 90% confidence. So it became so well known and so popular that he wanted to publish his work. Now, the problem is in 1908, in Ireland, Guinness breweries did not allow their employees to publish under their own name. So, what he ended up doing was he published his work under a pseudonym by the name of Student. So since this distribution was so successful and accurate in future calculations, he called it the student's T distribution. So the T doesn't really stand for anything, it's just a statistical notation. So if you have heard t-test, t-value, this is where the T is coming from. So it's called the T distribution, but it's also called the student's T distribution. And I'm going to share a blank screen so I have more room to write on. So if you recall, when I first talked about probability distributions, I said they depend on two types of data. Either we use discrete data. Does anyone remember what the probability distributions are if you use discrete data? And we have continuous data. So with discrete data, we had the binomial distribution and the Poisson distribution. We only learned those two with discrete data. And then with the continuous data, we focused on the normal distribution. Okay, so this is just getting you to recall things that we discussed in previous chapters. I also said there's something called the exponential distribution and the uniform distribution, both of which we will not be studying. So the normal distribution. Now I'm saying that there are a family of distributions that are based on the normal distribution. The T distribution is one of them. The F distribution is another, and chi-squared is another. So if you decide to take econometrics or economics 382, then you will learn about the F distribution and the chi-squared distribution. But for now, just know that there is a family of distributions that are based on the normal distribution, and the T distribution is one of them. So that's where this T distribution is coming from. The other thing I want to mention is that T distribution is not the normal distribution. It's slightly different because the shape of the curve is no longer normal, like the normal distribution. So let me go on back to our slides. So we were here. Next slide is saying, talking about William Gossett, discovered that when he uses standard error, so this is where the S comes in, the sample standard deviation, the shape of the curve was no longer normal. He called the new model the student's T, which is a model that is always bell-shaped, but the details change when the sample size changes. The student's T models form a family of related distributions depending on a parameter known as degrees of freedom. So I'll get to that. So that's how these different distributions really differ from each other. Something called degrees of freedom. So that's how the T is different from the F distribution, is different from the chi-square distribution. Okay, so moving on to the next slide. Now we can really look at the differences between the normal distribution and the T distribution. So let's look at the properties. First property states that T distribution is bell-shaped and symmetric. So that's the same thing. That's one of the properties of the normal distribution. But now I'm going to use a different color here. The dashed line that you see is the normal distribution. And the solid line is the T distribution. So now I can say that the T distribution, that solid line, has less area in the center and more area in the tails. Okay, so again, I'm saying the T distribution has less area in the center and more area in the tails compared to the normal distribution. The normal distribution is more bell-shaped. It has more area in the center and less area in the tails. Okay, something else I'm going to point out, these 2 points here. So these 2 points are my critical values. Now remember, we always shade the center for our confidence intervals. The 2 points are my critical values. So now I'm not dealing with Z tables anymore because that would be the normal distribution. I'm dealing with the T distribution. So that means I'm looking at plus or minus T, not Z, but plus or minus T. And I'm going to write a subscript. The subscript is n minus 1, comma, alpha divided by 2. So that entire thing is my subscript. So now what is n minus 1? Okay. So n minus 1 is my degrees of freedom. And alpha is level of significance. Alpha is the level of significance, or alpha is the risk level that can be tolerated. So those are the tails. That's what's going on in the tails. That's the area in the tails. So the two areas together would be alpha. And since this is symmetric, each tail would be alpha divided by 2. So now degrees of freedom, it has such a fancy term for something that is so easy to visually understand, n minus 1, sample size minus 1. So I said that the family of distributions that are based on a normal distribution, chi-squared F distribution, they are different from each other based on the degrees of freedom. So you will see that the F distribution could be n minus 2, n minus 3. It depends on sample size. So if you had a question, true or false, does degrees of freedom relate to sample size? What would you say? Do the degrees of freedom relate to sample size? Sure, yes. Yeah, that's the answer. So that brings us to the second property of the t-distribution. As number of observations in the sample size, in sample increases, so I'll start again. As number of observations in the sample increases, the t-distribution approaches the normal distribution. So if you look at the graph, if I start increasing n observations in my sample, if I start increasing n, now the t-distribution is going to be the normal distribution. So this is telling me that as n increases, it becomes the normal distribution, which should sound familiar. What does it tell you? Does this sound like something else you have heard? So this is really the central limit theorem. So the central limit theorem says that when n is greater than 30, any distribution that is not normally distributed approaches a normal distribution. It can be assumed to be normally distributed when n is greater than 30. So even if I'm originally dealing with a t-distribution that is not a normal distribution, if I start increasing the number of observations in my sample, I can automatically use the z-table because it's a normal distribution. So we have to remember that when we're dealing with a t-distribution. Okay, moving on to the next slide. So actually, I'd rather go to this. Yeah, okay, let's do this slide. So now confidence interval for population mean mu when sigma is unknown. So here we're saying that population standard deviation is unknown. A couple of assumptions, same way as we did before. First, the population standard deviation is unknown. We have to assume we don't know it. Second thing, the population is normally distributed. So we're assuming that we are dealing with a normal distribution. And if the population is not normal, then we use a large enough sample. So I'm going to start with the formula first. First, x bar plus or minus. So x bar is my sample mean, plus or minus my critical value. So the critical value subscript t subscript n minus 1 comma alpha divided by 2 times s over square root of n. So I'm going to rewrite this so you get to see it. X bar is my sample mean plus or minus the critical value of t. Subscript n minus 1, that's an n minus 1, comma, alpha divided by 2. And then the whole thing times s divided by square root of n. Now, s is my sample standard deviation. Remember, we don't know what the population standard deviation is. So Gossard came up with this formula and said, well, you can use a sample standard deviation as long as we incorporate the t distribution. And that way you can come up with an estimate, an interval with a lower limit and an upper limit. And you can actually estimate what the average is for the entire population. So quite significant and pretty simple. And you don't have to even memorize this formula if I show you how to use Excel. Okay, so I'm going to do a few things today. I'm going to show you how to read the t distribution table, and I will show you how to use Excel. So it's up to you to decide which method you want to use. They're both just as easy. So your choice. Okay, so moving on to the next thing. The next thing is to show you why we have degrees of and why we use sample standard deviation. So if you recall, the formula for sample standard deviation is this. In the numerator, it's the sum of x subtracted from x bar squared. So you take every value of x, subtract it from the mean, plus second value of x, subtract it from the mean, plus, and so on. Notice in the sample standard deviation, we have n minus 1. If I did the same calculation, so this is not a new formula. You've seen it before in previous early chapters of statistics. If I change the formula and I divided it by n instead of n minus 1, the value that I get for sample standard deviation is so minute, it doesn't really make sense. It's not a practical value to use when you're doing analyses and you're coming up with estimates. It's a useless value, really. So mathematicians said, well, why don't we divide it by n minus 1? And that's where this idea of degrees of freedom came about from this n minus 1, this formula of sample standard deviation. Now that I talked about this formula, I'm going to tell you that you're going to use Excel or you're going to use your calculator, and most of you have this function in your calculator to find standard deviation. Same thing with Excel. It can easily find standard deviation for you. You don't need to know how to access the formula. Okay, so we're going to start first with a simple example. Now, although it says poll, I'm not going to do a poll, but the example is just to find the critical value t. Okay, so starting with, suppose you have 15 items in your sample, or 15 observations in your sample, and your level of significance, alpha, is 0.05, then what is the critical value? So you're told the risk level that can be tolerated. You're told that alpha is 0.05, and you're asked to find the critical value. So now we know that you need to find this value t. So again, subscript is n minus 1, comma, alpha over 2. So I'm going to rewrite this as plus or minus t. Now what's my degree of freedom? So the question is, what are my degrees of freedom? Yes, 14 is the right answer because degrees of freedom is n minus 1. Okay, so let me just write that as 15 minus 1, comma. My level of significance is alpha. So that's 0.05 divided by 2. I'll keep it as that for now. And I have uploaded normal distribution tables on MyLab. So you've probably seen it, you've used it in your homework. So these are the same tables. but we only referred to page 1 and page 2. Now what you're looking at is page 3. I'm going to write here, this is page 3 of the normal distribution tables that you can access on MyLab under Course Tools, Document Sharing. Okay, so that's where you would find this. So on page 3, the first column says DF. DF stands for degrees of freedom. And then you have the subsequent columns. But the first two rows say two-tailed probability and one-tailed probability. When we're dealing with confidence intervals, we always deal with two-tailed probability. Okay, so always two-tailed probability. So we're going to start with degrees of freedom. In this example, we're told 14 degrees of freedom, 15 minus 1. So I'm going to go down to 14 and look at my 14 degrees of freedom. Then I go across to two-tailed probability. Alpha together is 0.05. So I have to take the alpha value as a whole for two-tailed probability, which is 0.05. So what's my critical value? Yes, Diana, that's right. So it's plus or minus 2.145. So make sure you all understand how to find the t value, the critical value. Okay, so this is how you would do it if you were looking at the tables. First thing is degrees of freedom, then go across to two-tailed probability using the total alpha value. Okay, so pretty simple, not complicated. It's just reading the table. So Priscilla, your question is, how do I know if a two-tail or one-tail? So one-tail probability we will be looking at in the next chapter when we talk about hypothesis testing. That's a one-tail test or a two-tail test. So that's for hypothesis testing. With confidence intervals, it's always two-tail probability. So I'm going to skip this slide because it's really telling you how to find the t-value. Same thing here, I'm going to skip it. Same thing here, it's showing you the table. So let's move on to this example. So this example, reading from the top, suppose we want to determine the amount of time spent by a customer on a Friday evening in December at a Starbucks restaurant within Queens. We take a random sample of 4 restaurants and find the following times: 132 minutes, 168 minutes, 118 minutes, 139 minutes. Construct a 90% confidence interval for the average amount of time. Now we saw a similar problem in the last class when we were doing confidence interval to estimate the average time. But what's different with this example? Do you notice anything different? So they both ask you to find the amount of time spent by a customer on a Friday evening. But there are differences. Judah, you're saying it's geospecific, so you're saying within Queens. Okay, so this one is a little bit more specific. The previous example didn't really tell us if it was in the United States, if it's New York City, if it's within Queens. We sort of assumed that we were dealing with a very large population. And in the previous example, we took a random sample of 100 Starbucks and calculated the sample mean for the 100, and then went on to use the value to estimate all Starbucks. In this example, you're told very specifically within Queens, so maybe the population is slightly smaller, and they took a sample of 4 random restaurants. 4. Okay, so now my sample is small, so that's one thing I noticed. It's less than 30, okay, because my sample size is 4. Anything else that you noticed? Shamaya, you said tells the different times. Okay, so for each of the 4, I have my individual values. So x1 is 132, x2 is 168, x3 118, x4 139. Okay, so that means I can use those individual values and come up with my average for the sample, standard deviation for the sample. So one main difference from this example and the previous example is that the population standard deviation is not given. It doesn't tell us what that value is. If I know what that value is, then I can use my previous method to construct a confidence interval using the z-tables. So when you're doing your homework, make sure, number one, is it the population standard deviation that is given, or is it the sample standard deviation that is given? If the population standard deviation is not given, you're going to use the t-distribution. Number two, your sample size is less than 30. Then you use the t-distribution. So two things happening, and they're in order for a reason. So in your homework, you might have an exercise where your sample size is greater than 30. However, the population standard deviation is not given. So that's the first thing. If your population standard deviation is not given, you have to use the t-table. Okay. So let's move on to the next slide. It's a blank slide, so I can start writing on it. Okay, so I know that this is the formula I'm going to eventually use. X bar plus or minus t times s over square root of n. So a few things I need to figure out first. So I need to know my sample mean is. And according to the question, x1 is 132 plus 168 plus 118 plus 139. David, what do you get for this answer? Jazib, do you have an answer for that? So as soon as we get an answer, okay, Dongyan, anyone else? The same value? Yeah. Okay, so 139.25. So this is telling me that the sample mean for the 4 restaurants is 139.25 minutes, right? So we have to remember that that's the unit we're dealing with. Now sample standard deviation. I'm going to put the formula here. Squared sum n minus 1. So if I had to do it manually, I would take the first value, which is 132, minus 139.25 squared, plus second value, which is 168, minus 139.25 squared, plus keep going, and then divide by n minus 1, and the whole thing square root. Or I can use Excel, and I'm going to make sure that's the correct formula I'm giving you. STDEV dot S, and then you select the cells. So for example, if I have in Excel, I hyped up my values of X. So I have 132, 168, 118, and so on. I would type, and I want the standard deviation, so I would type in stdev dot s open parentheses, and in the parentheses I would select the range of cells that I want the standard deviation calculated for. So I would select these cells. And can someone give us that answer, please? Red, you said 21.06. Anyone else? So we can confirm two people got the same answer. Yep. Thank you, Kathleen. You have the same thing. Okay. So now we have two things in our formula. We have x bar, we have s, and we also know the value for n. N is 4. And the question also tells us that we have to be 90% confident of our answer. So that's what we're going to use now to look up the critical value in the next slide using the table, right? So I'm going to show you from the table as well as Excel. You might want to take a picture of this when I go to the next slide because we won't be able to return to this. So the only thing left now is for me to find the critical value. Okay, so here we are. I'm going to just write down all the values that we had. So we had x bar of 139.25. S was 21.06. Okay. Okay. N was 4, and we're 90% confident. Okay, so this is information we have. Continuing now to find plus or minus e at n minus 1 comma alpha over 2. So now we need to find our critical value. So rewriting this first, plus or minus t. What's my degrees of freedom? Harun, okay, Kathleen Arzu, you say 3, 4 minus 1. And then alpha is 0.10. So make sure you understand where I'm getting 0.10 from. It's because I was told to be 90% confident. So alpha ends up being 0.10. So alpha divided by 2. Okay, now I'm ready to look up in my table. The first thing is I go to my degrees of freedom column and look up degrees of freedom 3. And remember, it's a two-tailed probability. Alpha total value is 0.10. So now what's my p value? Yes, 2.353. Okay, so I'm going to mark it here. 2. Any questions for me? Okay, so now I'm going to plug everything into our confidence interval formula. So x bar is 139.25 plus or minus critical value of 2.353 times S is 21.06 divided by square root of 4. What's the standard error of the mean? Standard error of the mean is just 21.06 divided by square root of 4. So does anyone have that answer for us? So just this part of it. 21. Okay, thank you. 10.53. Okay, 10.53. Now, what's the margin of error? So remember, margin of error is this entire right side of the formula. Margin of error is the same thing as sampling error. So I'm waiting for the margin of error or sampling error. And Dongyan, you said 24.78. Do you have 3 decimal places? Anyone else can confirm that's the same answer? The reason I'm asking for 3 decimal places, 777. We might have been rounding too early. If you round too early and you put your answer into Excel, it may or may not mark you as correct. So get into the habit of using 3 decimal places so that your final answer is accurate. So now this is what we came up with. This is really the answer to the question. The average amount of time is 139.25 minutes. So don't forget to put the unit. That's minutes. Plus or minus a margin of error of 24.77. Okay, so that's how you would calculate, saying this is your point estimate, 139.25 plus or minus margin of error. Now, in the next slide, I can go on to show you how to continue and do upper limit, lower limit, and the interpretation. But I just want to go back to Excel and show you how to do the same thing without the T table, without referring to the distribution table. And you'll get the same answer. Okay, any questions for me before I switch over? Let's see if you're right. Any questions before I switch over? Okay, so I'm going to share my Excel screen. Okay, so make sure you understand how to do this. Now, the formula was in that slide, so I'm going to type it in here. Actually, before I do that, let me put in these values: 132, 168, 118, 139. So it's only 4 values, right? And I have to come up with confidence dot T because I'm interested in the T table, and it's prompting me the values to put in. So alpha, it's asking for alpha. Now we said that we're dealing with 90% confidence, so alpha is 10. Standard deviation is 21.06. You already found that. And sample size was 4. So you already found that. And then I would just say enter, and that would give me the answer. But let's wait a moment. Let me actually not put the equal sign. I'll come back to this. I want to show you how we could have done the whole thing on Excel. So the first thing I need is the average. So I'm going to click on this and tell Excel, give me the average for that. So that's the average. So I'm going to write here, that's my mean. And then I want my standard deviation for the sample. So I'm going to go here and type in my standard deviation formula, which is standard deviation S, because I'm dealing with samples. And I'm opening the parentheses and selecting my range. That's the range, so I hit enter. So this is actually the standard deviation with the 3 decimal places, 21.061. And now I'm ready to type in my values for the confidence interval. Remember, you always put an equal sign so that Excel knows the formula. The first one in the parentheses is alpha, standard deviation, comma, n. And then I say enter, and that's where, Brad, you were right. So Excel is giving you 24.78 as your margin of error. So remember, this is not the final answer, right? This is just giving you the margin of error. It doesn't give us the lower limit and the upper limit, but you could do it on your own by saying it's 139.25 plus or minus this margin of error. Any questions for me? Okay, so your choice which one you want to use, Excel or referring to the tables, but I'm showing you both. And you can use either one. So the last thing for this example is to understand how to interpret your answer. Because you could do the whole thing and then get the interpretation wrong. So here's what we did last. Moving on to the next slide. So this slide takes you to one further step where you can come up with the lower limit and the upper limit. So you're saying that 139.25 plus or minus that margin of error, 24.78, I think. And then you get the lower limit and the upper limit. So you can see here that the population mean, mu, is predicted to be between these two values. Final thing is the interpretation. So this is the interpretation. It's not writing. Okay. We are 90% confident that the average amount of time spent by a customer on a Friday evening in December at a Starbucks restaurant within Queens is between this lower limit and upper limit. And don't forget the units. Any questions? Okay, so then I have a polling question here. Whoops. I'll give you a moment to read it, and I'll post the poll. The question is this a correct interpretation? So yes is true, no is false. Okay, another minute to answer, or 30 seconds. Okay, so I'm going to stop here. So you can see that most of you chose yes, and that is the correct answer. So true is correct. This is a different way of interpreting it, where you're saying that this is the average with a margin of error of this. So you could interpret it in both different ways. Last thing I want to share with you it's taking a while to load, is this. So this is actually at Guinness Breweries in Ireland. If you have the opportunity to go for a tour, you'll actually see William Gossett's plaque on the wall saying that he's a chemist and a statistician. He was the chief brewer. He came up with the students' tea test. And not something that I made up. This actually exists. What I'm going to do now is break you up into groups, and what I want you to do is do the same thing that we did. But before that, let me answer Armila's question. So you say that even though the calculation was done for restaurants, we can make a conclusion for all. Yes, so that's the whole beauty of the confidence interval. that just because your sample is for 4 or your sample is for 100, you can apply this confidence interval to anything and you make up your conclusion for all restaurants, for the entire population. So in today's class and the previous class, I focused on coming up with an average, predicting an average. In the next class, we'll talk about proportion, percentage of people who think a certain thing. So you can do it for mean and you can do it for proportion, and you can do it for any discipline. It doesn't have to be the specific examples that I'm giving you. It could be for anything. So that's the beauty of confidence interval. So now what I want all of you to do is when you go into your little groups, you're going to talk about the last time you commuted to campus. Maybe fall 2019, maybe early spring. So you're going to tell your fellow group members how long it took you on an average to come to campus. What was your individual commute time? So once you get your individual commute time, so let's say there's 8 of you in a group. If you have, so collect all 8 commute time, and those are all your X values. So you're going to use Excel to do this, right? And then you're going to come up with the average for all those X values. So the same way I did it with Excel, and I'll show you in a moment. And you're going to come up with your sample standard deviation. And then you're going to plug in the Excel formula to come up with a confidence interval. And then you're going to come back to the main room and say that for our group, the average commute time is between this lower limit and this upper limit. Okay, any questions for me? So the confidence level, I'm going to say, is 95% confident. So I want you to be 95% confident. So I'm going to share my Excel screen for a moment. Okay, so sharing the Excel. So let's say we have a new sheet. Okay, so you have, this is, and person number 1 takes 30 minutes to come to campus. Someone else takes 20 minutes, someone else 60 minutes, someone takes 70 minutes, someone is really close by, 15, and so on. So let's say those are the people in your team. Next step is to calculate the average. So you say you want the average from here to here. So that's correct. I'm going to highlight this so we know that that's an average. And then you sample standard deviation. So you say equal sign STDV dot S open parentheses, and this is the range, close parentheses, and you have that. Okay, I made a mistake here. I spelled it wrong. And I have my sample standard deviation. Then I need to come up with my confidence interval. So according to the formula, it was confidence dot T open parentheses. Now I'm saying 95% confidence. So I want alpha 3.05. Standard deviation I calculated was 23.717, and sample size was 1, 2, 3, 4, 5 people in my group, and this is my margin of error. So I have one more step to do, right, to calculate my lower limit and upper limit. So this is what I want you to do. You're going to ask each other what the average commute time was for you when you used to come to campus. Okay, so bear with me while I put you in breakout groups. Any questions before I split you up? Okay, there should be about 10 of you in each group, so you 10 values for X. When I bring you into the back into the main room, it's going to be in about 10 minutes. So at 1:23, I'll bring you back, and I will need to know how many shared their information in your particular group. Okay. Okay, so everyone's back. I apologize for the noise here. You can hear it, but can we have group one start? So you might not know who is group one, but I'm just going to put down and then you go ahead and write down what you found for your lower limit and upper limits. Okay, so that's good. Group one, you fixed it. That's 14 minutes. Group three, that's fine. If your sample size was 8. Oh, that's what you meant. Okay. N is 8. Got it. Yeah, that's a long commute time in group three. Two more groups to go. So we have two groups that did not put in their lower limit and upper limit. Does anyone have information for group 4 and group 6? Okay, then group 4 and 6 won't be able to get credit for participation today. Okay, so looking at the values that we do have, this is information that, let's say, Queen's College can use. So now they know if there's a commuter that is close by or far away, they know how to advertise and market to those students. So Queen's College could say that most students live within half an hour. So it's quite possible and accurate for Queen's College to say something like that, because we can see here that it takes about half an hour. It takes about half an hour. Okay, this takes about half an hour. So it's a fair statement to make. So these numbers don't seem right. So you might want to check those numbers again. But this is how confidence intervals can be used. Okay, any questions for us? Okay, I'm going to stop recording.